So now electric field due to a this electric field due to a discrete distribution of charge. Discrete distribution of charge. Suppose, let's consider that a number of charges are placed in free space. A number of charges are placed in free space. Q1, Q2, Q1, Q2, Q3, up to Qn. Up to n number of electric charges, point charges, are placed in free space. And we want to find out the resultant electric field at this point P due to all these charges. Is it okay? There are two ways to do this. One is by using Coulomb's law. Using Coulomb's law, I can find out the force exerted. I can put a test charge over here. And using Coulomb's law, I can find out the force exerted at this point due to Q1. I can find out the force exerted on Q2 or on Q0 due to this Q2. I can find out the force exerted on Q0 due to this Q3 and up to Qn. And then I can use the relation that electric field is defined as force experienced per unit test charge. In that case, I can find the electric field at this point P due to Q1. I can find out the electric field at this point due to Q2. I can find out the electric field at this point due to Q3 and so on. Okay? But we can do it in the shortest way. We can do it in the shortest way because we know that the relation for electric field at any point due to a charge Q is given by E is equal to in magnitude, E is equal to 1 by 4 pi epsilon naught into Q by R square. Right? This is the electric field at any point due to a source charge Q. Now, so here also we are going to find out the electric field at this point P due to all these charges. So according to the principle of superposition, okay, we use the superposition principle here. The resultant electric field at this point P will be the vector sum of all the electric field at this point due to Q1, due to Q2, due to Q3 and so on up to Qn. Are you following that? Now according to the principle of superposition, electric field at this point P will be the vector sum of all the electric fields at this point due to Q1, due to Q2, due to Q3 and so on up to Qn, right? Yes. But see, we have used the word discrete here. Discrete means the field produced by Q1 and the field produced by Q2, they are not going to interact with each other. When we are considering the electric field at point P due to Q1, we will assume that Q2, Q3 and so on up to Qn is absent. Are you getting me? Yes. Let's assume that we are assuming that when we are finding the electric field at point P due to Q1, we will assume that the remaining charges are absent. When we are finding the electric field at point P due to Q2, we will assume that Q1, Q3 up to Qn are absent. And when we are finding the electric field at point P due to this nth charge, Qn, then we will assume that all the charges from 1 to n minus 1 are absent. Are you getting me? Yes. So that is the mean of discrete distribution of charge. So the electric field produced by each of those charges, they are not going to interact with each other. Is it alright? So there is a charge Q1, okay, which is placed at a distance R1 from P. there is a charge Q2 which is placed at the distance R2 from P. There is a charge Q3 which is placed at the distance R3 from P. And so on, there is a charge Qn which is placed at the distance Rn from P. Then from the relation for electric field at a point due to a source charge, we have electric field at point P due to charge Q1, E1 will be given by, okay, we can consider in vector form, okay, let's say unit vector R1 cap be the unit vector representing the direction, representing this direction. Let R2 cap be a unit vector representing this direction. Let R3 cap be a unit vector representing this direction. Let R1 cap be a unit vector representing this direction, representing the direction of the electric field. Okay. Oh, see, very important, very important point here. The most important point of the electric field. Suppose you have a point positive charge placed in free space. Then this charge is going to create a field around it known as electric field. But what is the direction of the electric field? For a point positive charge, the electric field is directed radially outwards. The electric field is directed radially outwards. R-A-D-I-A-L-L-Y, radially outwards. Is it okay? Electric field is directed radially outwards. But these are imaginary lines. It doesn't mean that if you place a charge, you can see those lines coming out from that charge. No, we cannot see that. These are just imaginary lines. Is it okay? No, it's just imaginary lines. So, for a positive point charge, the electric field is directed radially outwards. It's directed radially outwards. Alright? And for a negative charge, and for a negative point charge, the electric field is directed inwards. Electric field is directed inwards. Now, when you place a when you place a positive test charge, you know what is test charge already. When you put a test charge in this region, this test charge will go away following this path. Okay? It will go outwards. Now, when you place a test charge in this region, that test charge will go outwards. So we can say that the electric field, okay, due to a point positive charge is directed radially outwards. Now, if you place a test charge in this region, then this test charge will be carried inwards towards this source charge, negative source charge. Are you getting me? So for a positive charge, the electric field is directed outwards, and for a negative charge, the electric field is directed inwards. We are going to study about the properties. I will discuss. I'll discuss like in much detail about that. Okay. Yes.
Suppose the test charge. The test charge. Suppose it is negative. Then like.
No. In order to determine electric field at any point, no, we always consider a test charge which is positive, and whose charge is vanishingly small. Okay? Yes. We have created this theoretically, no, not for experimental purpose. So where were we? Electric field due to a discrete distribution of charge. So a number of charges are present in free space. I'm repeating again. And we want to find out the electric field at this point P due to all these charges. Now, according to the principle of superposition, electric field at the point P will be the vector sum of the electric field at this point due to all these charges. Now, we have written here discrete distribution of charge means, okay, when this charge Q1 is interacting at this point, okay, we will assume that when we are finding the electric field at this point due to Q1, we will assume that the remaining charges are absent. Okay, here we are assuming that we are imagining that this Q1, Q2, Q3, Q4, Qn, they are not interacting with each other. Is it okay? Now, if they interact with each other, then things becomes so complex. Alright, so we are assuming that this field and this field, they are not interacting. This field and this field, they are not interacting. We are assuming that way. Only then we can find out the resultant electric field here. Are you getting me? Yes. So suppose this point P is placed at a distance R1. Okay, and we have to place a test charge in order to determine the intensity of the field at this point B due to Q1, right? Okay. Suppose NC, the direction of the electric field will be directed radially outwards. Let the direction be represented by unit vector R1 cap. Now, if this is a positive charge, this is also point positive charge, electric field will be directed radially outwards. Let the direction be represented by R2 cap. Is it okay? And the distance, we can take it as R2. Similarly, let Rn be the distance of this point from Qn. And the electric field at this point due to Qn will be directed radially outwards. So let the direction be represented by Rn. Okay, so this is in magnitude. In direction, A is equal to 1 by 4 pi epsilon naught into Q by R cube vector. Or we can do like this. A is equal to 1 by 4 pi epsilon naught into Q by R square with unit vector R. Right? We can write it in those ways. So let E1 be the electric field at point P due to Q1. So that's 1 by 4 pi epsilon naught into source charge. Q1 is creating the field. Q1 upon square of the distance R1 square, and the direction is represented by R1 cap. E2 is equal to 1 by 4 pi epsilon naught into Q2 upon R2 square with unit vector R2 cap, and so on. En will be equal to 1 by 4 pi epsilon naught into Qn by Rn square with unit vector Rn cap. So the resultant electric field at the point P will be the vector sum of all these fields created by all these charges. Okay? So E1 plus E2 plus E3 and so on up to En. E1 1 by 4 pi epsilon naught into Q1 by R1 square unit vector R1 cap. E2 1 by 4 pi epsilon naught into Q2 by R2 square unit vector R2 cap, and so on up to En 1 by 4 pi epsilon naught into Qn by Rn square unit vector Rn cap. In short, I can take 1 by 4 pi epsilon naught common, right? So, or I can write summation I is equal to 1 to n 1 by 4 pi epsilon naught Qi, Q1, Q2, Q3, I is equal to 1 to n. So I, Qi, upon R1 square, R2 square, up to Rn square. So Ri square, where I is equal to 1 to n, with unit vector Ri cap. So this is the resulting expression for electric field due to a discrete distribution of charge. Electric field at a point. Point ektadi, when a number of charges are interacting there. Alright? Okay, this is done. Okay, I want you to make a note of it. Okay, after that I will go for another relation, a very important relation.